Hi there, and welcome to insideQuantum, the podcast telling the human stories behind the latest developments in quantum technologies. I'm Dr. Stephen Thompson, and as usual, I'll be your host for this episode. In previous episodes, we've talked about the theory behind quantum computers and the details of some of the hardware platforms that can be used to build them. But engineering the quantum properties of new materials for new technologies is a concept that goes far beyond quantum computing. For example, by tailoring the electrical or magnetic properties of materials at the atomic level, we can potentially build the new and much more efficient technologies of the future. Today's guest works on building quantum materials from the ground up. It's a pleasure to be joined today by Dr. Jennifer Fowlie, a postdoctoral researcher in the Department of Applied Physics at Stanford University and the Stanford Institute for Materials and Energy Science, part of the SLAC National Lab. Hi Jennifer, and thank you for joining us here today.
Thank you for asking me to be here.
So, before we get into the details of how to build materials atom by atom, let's talk about your journey to this point, and let's start right back at the very beginning. What first got you interested in quantum physics?
Yeah, I think I was interested in a lot of different aspects of science as a child, from basically as early as I can remember. One memory that does stick in my mind, I think I was at the beginning of high school, so probably age 13 or 14. I had a Guinness Book of Records, and one of the records that they wrote about in this book was the longest time dilation experienced by a human. And it was some cosmonaut, of course. And I wanted to know what a time dilation was, so the next day I went to school and I asked my science teacher, what's a time dilation? And I think my science teacher immediately brought me to the physics teacher. Please explain to Jennifer, what is a time dilation? My physics teacher made a good effort to try to help me find the answer, looking around online. And to me, I couldn't believe that was a real thing and not a magic thing. So while it's not really quantum physics, and it's certainly got nothing at all to do with what I do on a daily basis now, it definitely attracted me to physics. So when it came time to kind of decide what I was going to do after school, for university studies, I was very motivated to do physics. I think I also felt a little bit of pressure to do something a bit more vocational. So I also applied for engineering positions, but I did end up going to do physics. I think because my physics teacher had convinced me that I could do physics first and then change to engineering later if I wanted, and it would be much harder to do engineering first and then try to switch to physics. So that's how I ended up deciding to do physics as an adult.
So then, at what stage did you decide that you wanted a career working in quantum physics?
Yeah, I don't think I ever made a conscious effort to have a career in physics. I wanted to study physics at university. I did do that. Then I finished my undergraduate degree and I wanted to study more. So I did a PhD, and then I wanted to do more. And I'm still doing it now and still trying to do more. It's reaching a bit the limit of how far you can go without actually admitting that you're trying to have a career. But yeah, I never made a conscious decision, I think. I just followed what I was interested in at every step of the way.
So for you, it was always the questions, it was always the science that drove you, and the career was the vehicle that allowed you to answer those questions.
Yeah, I mean, I suppose in the end you need to get paid, right? So yeah, a little bit. But it has been very nice. I've been able to travel all over the world and meet all kinds of interesting people, and not a lot of careers allow you that kind of freedom and flexibility.
Yeah.
So I think we're kind of lucky in that respect.
Yeah, absolutely.
Yeah.
Well, speaking of your career, can you tell us a bit about how you got to where you are now and give us maybe a quick summary of your career to date?
Yeah, so the position I have now as you said, is in applied physics, and it's in this Institute for Materials and Energy Science. So I really do materials physics. How I got to that point, it's a little bit convoluted, but when I think back, when I started university, started my my undergraduate degree, I think I wanted to be a theorist. I always saw myself as doing physics with a pen and paper, not in a lab, which is what I do now. I think I was a little bit in denial about how much I liked to be in a lab. I do remember being very, very intense about my lab reports when we were doing whatever it was called, like laboratory skills for physicists or whatever. I wrote these huge lab reports. I mean, I spent so much time on those things. I don't know if this is true, but one of the demonstrators, one of the assistants, told me afterwards that after my report, they put a limit on the number of pages you could submit. Because I submitted a 90-page report on semiconductors.
You know, they did do that because of someone, and I don't know who it was.
Was it? It could have genuinely been me. He was quite cross at me when I submitted that. I thought he would be happy, but he was not, because he had to read it.
I guess they don't pay them well enough to mark a 90-page lab report.
No, I think that, and after having been a lab demonstrator for undergrads, I totally get it now. But at the time, I was super proud, and but I used to really enjoy doing those. But I think the moment that I really realized was during a class that was called transferable skills. So the idea of this class is to instill some kind of transferable skills into these physics undergraduates. I think it's actually really good, and it's not a class that all universities do, but my university did. So what you have to do is you choose a topic from a list that they give you, and then you have to write a review article, and you have to give a presentation. And there's also a bit of preparation for these things. You have to read papers, and you have to discuss with an advisor. So they assign you an advisor who knows a lot about that topic, who can kind of guide you through it. So I looked on this list, and there were it was a very wide variety of topics that you could choose. For example, there was potato batteries, how rainbows are formed or whatever. The one that attracted me was the one with a title that I didn't understand at all, which was topological quantum computation.
That's a long way from potato batteries.
Yes, it is. But I thought, well, I'm going to go for the one that sounds the most difficult. They send you to discuss with your advisor. So I started reading papers and started going to these meetings with this advisor, and he was really heroic, and he really wanted me to understand the theory. And every single time we would meet, he would start at the beginning with the theory of, braiding Majorana quasiparticles, quite hardcore theory, very hypothetical stuff here. And then I was reading papers and really trying to understand. But I found when I was reading these papers some big names, people who have actually contributed a lot to that field. And I thought, you know what I'm going to do? I'm going to send an email to one of them and see what they say. I'll just ask them one question, because for sure they're busy, so I'll just choose one thing to ask. And maybe I'll get an answer. Would be cool. So I decided I was going to send an email to a man called Michael Friedman, who is a mathematician, who at the time, and I think perhaps still now, was the director of Microsoft's effort on building one of these topological quantum computers.
So a real big name then.
A really big name, yes. And I thought, well, I'll ask just one question. So the question that I chose to ask, which in hindsight for me was really clear that I was not going to be a theorist, was, how do we build one of these topological quantum computers? What kind of material system do you need for that? So that was the question I asked. That should have been a huge hint for me. The next time I met with my advisor, I explained to him, I wrote an email to this guy, Michael Friedman. Do you know him? And so my advisor said, okay, he's probably really busy, so he probably will not see your email. And even if he sees it, he probably won't have time to reply to you. And in fact, he probably has a secretary who reads his emails for you, so I really wouldn't expect a reply. He was really quite shocked and a little bit maybe embarrassed for me that I had done that. And I had to stop him and interrupt him and say, oh, no, he replied after 10 minutes. Yeah, he replied straight away. Yeah, he replied to me straight away. And his answer was, I think the most likely material system is a px plus IPY superconductor. And I was immediately like, what's a px plus IPY superconductor? And I think that was really the moment that I thought, well, if I'm going to do anything useful in this world, I mean, you can talk all you want about hypothetically braiding these Majorana quasiparticles, whatever. If I'm going to do something useful, I need to do the hardware stuff. I need to really get into materials. Mm-hmm. So I think that was really one of the main points for me. And then afterwards, I did an internship in growing thin films of these quantum materials, not always superconductors, but just various materials. And then I did that for my PhD, and now I'm doing that as a postdoc. And yeah, I think I'm really, although I trained as a physicist, really close to material science now.
It's interesting that you started on the theoretical side. Maybe I'm a little biased. I have the impression a lot of people who end up in theory don't start there. They start by doing some of the more flashy things or some of the more practical things, and then discover maybe they don't enjoy it, maybe they're not good at it, maybe their first love is maths. It's interesting to hear from someone who started on the theory side and then had almost the opposite reaction, that it was maybe too far removed from the world and that's not what you wanted to do.
Yeah, I think that the theory for me always seemed quite mystical. And all of the most famous, most iconic physicists are theorists. Mm-hmm. I don't think that's a coincidence. They just seem to carry a little bit more, I don't know, mystery, something kind of cool.
I guess there's more scope for theorists to have kind of crazy ideas and then leave it to the rest of the world to put the pieces together, and then and then it's an engineering problem, right?
Yeah, and maybe to have a big impact alone.
Yeah, that's true. That's true.
Yeah.
Certainly in the early days of quantum physics, I guess, it was very much the lone genius stereotype. Even the experimental groups were small, right? Like,
this is true.
Yeah.
This is true. But at least I believe the experimentalists probably at least had a couple of people to work with.
Yeah, I'm trying to think of the
technician type.
Yeah, the famous Rutherford nucleus experiment. I can't remember the name of the other two who were involved, but there were at least three of them, right? There were Rutherford calling the shots, and then several people working in the lab. Compare that with his contemporaries, Pauli, Heisenberg, Dirac. They were all working alone, as far as I'm aware.
Yeah, that's what I've heard. I mean, I'm sure they had students. They had students for sure, actually.
Yeah, at some point.
Students doing stuff.
Yeah.
So who knows who actually came up with these things.
Yeah, fair point. Well, if you weren't doing the job that you're doing now, what do you think you might be doing instead?
I find it hard to imagine doing something different to what I'm doing now. So I feel like I would be a researcher, but perhaps in engineering and either material science or maybe electrical engineering, since right back at the beginning I almost did do engineering. Mm-hmm. So maybe that. Otherwise, I'm really not sure. I would hope that I would have had a job that I would have liked, that would have allowed me to talk to people, especially young people, and through the form of teaching, and tinker a bit. That would have been my hope for my alternate reality self, who didn't become a physicist.
It sounds like you're right where you're supposed to be in that case.
I'm very happy where I am, yeah, I am actually.
So if I were to summarize your research work in a single phrase, I might very broadly pick quantum materials. Can you break this down for us? What does that mean? Yes.
So quantum materials, I think, is very broad, in fact. I would say that there are different degrees of how quantum a material is, starting from something very stupid, which is simply that all materials are quantum because they're made of atoms, and atoms exist because of quantum mechanics. The next step really is, though, that materials that have properties that can only be explained by quantum mechanics. So this is different from materials that have nice properties, but we have classical approximations to them. So for example, semiconductors, the band gap is inherently quantum, but we don't really need quantum mechanics to understand it. A lot of our conventional electronics are quantum in the sense that, for example, LEDs and photodetectors rely on the quantization of energy. But yeah, quantum materials really means that you have phenomena that are appearing in these materials that can only be explained when you consider electronic wave functions. So the wave nature of matter there. And a good example of this is superconductivity, which arises in many materials. And this is electrons talking to each other over long distances. It's entanglement, really. So this is inherently quantum. It can only be explained by quantum mechanics. So quantum materials is materials like that, I would say. And a lot of magnetic materials as well, maybe except for the very simplest, for example, ferromagnets are quantum. They have to be. And then I would make a further distinction between quantum materials, which sort of encompasses all of what is known as condensed matter physics, typically. It's kind of a rebranding of condensed matter physics. I would draw a line between that and then materials which can be used for quantum technologies, which are, they can be semiconductors, or they can be more what we usually think of quantum materials, which often involve strong electron-electron interactions as well. So yeah, that would be my overall kind of breakup of different types of quantum materials. And then I would just add that quantum materials is very, very large as a field. And there are people working quantum materials in chemistry departments, physics departments, engineering departments, material science departments, electrical engineering. All of this comes in, all offering their own thing to try to understand and use quantum materials better.
Can you tell us a bit more about what it is that you do then? What's the big picture goal of your field, and how does your work fit into that?
Well, so what I do is I grow thin films of materials. And when I say thin, I mean they are really, really thin. They're as thin as can be. They can be down to one atomic layer. That's how thin. And we're interested in their fundamental physical properties. I am primarily working with physicists, so that's really what we're looking at. But since these are already thin films, they're already very close to being integrated in devices. And almost any sort of electronic or conventional electronic application that you can think of requires thin films, whether it's through coatings or layers of semiconductor to make a transistor. It needs thin films. So that's my day-to-day life. But this is really situated within this larger field of quantum materials. And I would say that the main challenges for quantum materials are there's probably two. The main challenges or main goals, let's say. Probably two, but they're very broad. So the first one would be to understand fully all of the properties of matter, so fundamental physics here. And kind of along with that, to be able to then create whatever property you want that you can think of with whatever specific characteristics you like. That's really fundamental physics there. And then the other side of it is really the application side. So to take the quantum materials that we have and try to make them useful for people. So that means not only having the correct properties, but with convenient operating conditions, scaling up, not just in size, because from lab scale, we spend hours and hours making something really small. You can't really start selling that. At least not for something that's affordable. So scaling up physically, but also scaling up so that the costs are reduced. And I would say along with that, in a way, is something that is really, really important, but it's not something that many people think about, I think, especially not in physics, is to try to have materials for our future technologies that are based on compounds that contain elements that are not running out. So there are some elements that we are using that our smartphones are full of these elements: indium, gallium, arsenic, and they're really scarce, and it's going to be a problem in the future. Some other elements also are from conflict sources, so parts of the world where it's really not good to have mines and politically not easy also to access the raw materials. So for example, since I mentioned smartphones, on a touch screen you have this coating which is typically indium tin oxide. Indium tin oxide is used because it's transparent, so you can see the screen behind it, but also it's conducting, so you can use a touch screen. So indium is really problematic, and there's a huge effort in the engineering community to try to find replacements for indium tin oxide. So this whole thing is trying to find something that's as transparent and as conducting, and also made from elements that are abundant, earth-abundant elements. Yeah, and I think, so quantum materials really is a very broad field which covers a lot of different types of materials and essentially all of what was commonly known as condensed matter physics. But it also covers materials that can be used for future quantum technologies, which means what will become the platform for qubits, which will be in your quantum computer. So I do hope that the researchers who are working on developing quantum computers have that in mind. I know that it's not something that they have to really think about right now. It's not an immediate issue for them. They have definitely other issues to work on first. But before too long, I really think that needs to be addressed.
That's a really interesting point, because coming from a more fundamental physics background, I guess, I talk with people who are working on quantum computers, and there it's always about, can you engineer these properties, right? Can you protect your qubits? Can you do the operations that you need? I'm not sure I've ever heard anyone talk about that. Can we do this in a sustainable way? Even when they talk about scalability, it's more, can we build a computer that can do the right number of operations?
Yeah.
Can it be big enough? They never really necessarily talk about manufacturing stability or scalability. I've certainly never had anyone talk about where they source the materials. The materials are almost an afterthought, I guess. The engineering problem after the more sort of fundamental, in air quotes, problem of how do you manipulate the qubits is solved. There must be some material that can do it, but
that's correct. That's for sure correct. I mean, there's a hierarchy of issues that you need to address, I think. I don't think it does any harm for those folks to actually have that in mind.
Absolutely,
at this point, that in maybe a couple of decades they will have to address these issues. But no, for sure there are other things to do first.
Do you think this could be one way to distinguish the different, for example, quantum computing platforms that we have? We have these, Majorana-based approaches, superconducting qubits, and so on. Do you think ultimately it's not going to come down to the performance, to the noise sensitivity, but maybe just going to come down to what materials can we make these from, which can we actually source?
It could be. So for the Majorana one, I mean, so there are two material systems that are commonly thought to be possible as platforms for these topological quantum computers. One is a so-called chiral superconductor, which is this px plus IPY that was introduced to me all those years ago. And there's no clear evidence for chiral superconductivity in any material so far. So I don't think in that case there's any harm in looking specifically or trying to focus our research efforts specifically in materials that we know are not going to be made of scarce elements. Unfortunately, one of the leading candidates is strontium ruthenate. Strontium is quite abundant at the moment, but it is used a lot, so it's running out. And ruthenium is already quite scarce, so that's not good. And then in the other materials platform, you're mostly thinking about quantum spin liquids, which is a specific type of magnetic system. And the most popular candidate for a quantum spin liquid at the moment is something called ruthenium trichloride. And chloride is fine, there's plenty of chlorine, but again, you have this ruthenium. So I think as fundamental researchers of fundamental physics, there's no harm in us sort of, if we have to choose a new research direction, maybe lean more towards ones that are looking at materials not made of things like ruthenium.
Yeah, definitely. That's a really interesting perspective that I haven't heard from anyone on this topic before. So you mentioned these different materials that are quite scarce, and
yeah.
there might not be many materials that have these properties. Is it still valuable to study these materials, to learn to build other ones or identify other ones that might have these properties?
Yeah, sure. Of course, it's interesting to do that. I think if you have a choice and everything else is equal, go with whatever material is least scarce. Mm-hmm. But of course, I mean, it's interesting to look at all types of materials. What we learn from one will allow us to predict properties in other materials, and we can kind of extrapolate and interpolate. We have the whole periodic table to play with, so we just can think what happens if we just increase the ionic radius and go this way on the periodic table, or increase the number of electrons and go this way. And so I think it's very useful still.
Is the ultimate aim to have almost like a dictionary, so that one day someone can say, okay, I want a material that has these 4 or 5 different electronic properties, and then some computer database will just say, okay, you want exactly these elements in this ratio, and we'll grow you the film?
Yeah, there's a huge computational effort in trying to simulate quantum materials, and more importantly to simulate what their properties are going to be. And then if you kind of do that in the reverse, you can say what property you want, and then your computer will come back with which material you need to look at. So a lot of computational physicists and material scientists actually have incorporated AI into their calculations to sort of try to do that. Yeah, huge effort on that. It's very important. We call that, depending on who you ask, dialer property, or materials by design, or functional properties. Yeah, functional materials, I should say. And these are the kind of names that we put into our grant proposals, but it does sum up what it is that we want to be able to do. So that is definitely one of the large goals of the field, really more in the fundamental side, but definitely leading into applications.
Is there a lot of interplay between experiment and theory in your fields? Is it more led by one or the other, or is it very much a case of both of them advancing equally?
Yeah, there's a lot of interaction and feedback constantly between physicists, material scientists, and computational material scientists and physicists. So especially, I think, for people like me who grow materials, it takes a long time sometimes to get good materials. So after you start trying to grow something, it can take weeks or months before you finally get something good after tweaking all the growth parameters. It helps a lot to work with computational material scientists at that point, just to help you be a bit more targeted. You can use that to help you decide which materials to grow, and you can also use that to help you figure out where in parameter space you should look to optimize the growth.
I see, okay. And then once you've grown these samples or obtained these samples from somewhere, you talked about characterizing their properties. How do you actually go about doing that? What sort of experimental equipment and experimental techniques do you use to answer these kinds of questions?
Yeah, there are almost more techniques to characterize materials than there are materials at this point. It depends what properties you're interested in. So let's say this example I gave, indium tin oxide, which is a transparent conductor. If you're going to try to find a new material to try to replace ITO, you would want something that's transparent and you want something that's conducting. So it's pretty clear what you have to use to characterize. You need to measure its resistivity, and you need to try to pass light through it and see what the transmission is. So that's very obvious. I think for fundamental physics, it's often less clear what we're actually interested in, and I think we're always hoping that we'll just to measure something and we'll find something interesting. So we're not always very direct when we're choosing which techniques to study our materials with. But you can use a whole range. So what we would normally do as the first steps would be resistivity. So just put contacts in your sample and measure that. Also check the magnetization. Mm-hmm. And you do these things as a function of temperature, because we are, unfortunately, in a field where lots of interesting things happen, but they're happening at very low temperature. So we use cryogenic measurement of those things. We use spectrometry and spectroscopy. So that's using light to try to probe different properties of your material. And then something that I do quite a lot of is to go to large facilities. So there are labs throughout the world that are usually funded by the government, which have very specific measurement setups that are so big and so expensive and so difficult to run that you can't just have one at every university. Mm-hmm. So you go to this one place and then you do very intense measurements for a few days. You have to be very intense about it because you only get a few days. And this includes synchrotron light sources. So this is very highly coherent X-ray light photons that are created in this particle accelerator. So there's a lot of synchrotrons throughout the world. And muon and neutron sources. So this is small particles now, not photons, but really matter that you're putting into your sample, watching how it scatters or watching how it gets implanted and decays. And these are very important for example, the chiral superconductors and quantum spin liquids and things that can eventually be possibly used for topological quantum computers. And then there's also high field labs, so you can, with a small lab in a university like the one I work in, you can have reasonable magnetic fields. Up to maybe 14 Tesla is affordable and doable. If you want to go higher than that, you need to go to these high magnetic field labs. So for all of these facilities, we have to make proposals, and we have to justify why our materials are interesting enough to take up some of their precious magnet time or synchrotron time, and then we go over there wherever it happens to be and do very intense measurements on that.
There's a certain kind of irony in having to use large international facilities to study very small, very thin samples.
I've often thought that, because you can go to one of these neutron diffractometers. If you ever have the chance to visit, I strongly recommend it. Like a huge circle of detectors, and right at the very center is your tiny sample. And my samples are, let's say, 5 millimeters by 5 millimeters. You can't see it from the edge of the detectors. But all of the machinery, because that example, there's a lot more than just detectors around. There's everything that created the neutrons in the first place. Yeah. All of that, just for your teeny tiny sample. It's kind of humbling, actually. I like it, though. I like it.
Historically speaking, physics has been a field dominated by white cisgender men for a very, very long time. Hopefully things are changing these days, but there is still a very long way to go before we reach any kind of equality. In your experience over the course of your career, have you seen things change at all? Are things changing for the better? And you've also worked in several different countries. Have you seen different attitudes towards diversity and equality in the different countries where you've worked?
Yes, I have seen a difference between different countries. So I did my undergraduate degree, of course, and I grew up in Scotland, and then I did my PhD in Switzerland, and then I moved to the US, to California. So I think where it has been the best has been in California. When I look around the auditoriums during our seminars, we do have quite a lot of women. I know that the university makes a big effort to actually recruit a diverse cohort of graduate students every year. My concern with that is just that they only care about getting them in, and then they don't care so much about keeping them there, making sure they're happy and thriving, and and trying to set them up for their best possible life, whatever it is they choose to do. And I think, just speaking about all kinds of historically excluded communities, we have always these power imbalances, and it is the responsibility of the people who have more power to try to fix that. And it should not be put on the shoulders of the people who come from those communities, absolutely not. So the problem of not enough women staying in physics, which is clearly a problem, and the ones that do stay in physics have a rough time of it often, that's a problem for men to solve. And I think that as a woman in physics, the best that we can really do is to acknowledge that there is a problem and keep talking about it. And then I would extend that to the other communities that we also need to help to boost.
Yeah, that seems sensible. I guess the more people who are aware that there is a problem, the more people who hear people's experiences and maybe come to the realization that there is a problem, the more impetus there will hopefully be to solve it. Although I suppose the issue there is the people who have the power to solve these problems are also the ones who are in a position of power within the system that
favored them in the first place.
Yes, exactly. So
exactly.
There's a paradox in there somewhere that I don't know how to resolve, but I hope that one day someone figures that out.
Yes, I know. I think that yes, the first thing is really to not be comfortable with it, to always talk about it. And people are going to get fed up of hearing about it, but you have to still talk about it. And I think I've heard too many senior women, not just senior women, let's say, I've heard too many women say, oh, I've never experienced any kind of sexism, misogyny, sexual harassment. I've never experienced it. And they're not saying that they don't believe the people who do report it, but I think it's honestly damaging to just say that in the first place. I don't think that's helpful. That's not called for. When you're asked to comment on how you feel about the gender diversity in physics, it's not helpful to say that you've never experienced it. Just don't say anything at all, I think, at that point.
Yeah.
And I also don't think that they have the evidence that they've never experienced it. They don't think that they've experienced it. Guaranteed they have.
In terms of perhaps people saying things behind their backs that they're not aware of?
Things like, well, she only has that position because she's a woman and they had to hire a woman. Or just simply opportunities that they were never offered. How do you know you were never a victim of discrimination if that discrimination took the form of someone not reaching out to you to ask you to come and give a colloquium or something? How do you know? You just can't. You cannot know for sure, so don't say that, I think, is the key.
Yeah, that's a really good point. One final question to wrap up with then. If you could go back in time and give yourself just one piece of advice, what would it be?
I think that is a great question, because I hope that it reminds people that you can still give yourself advice now. And I would try to, apart from giving myself specific advice on what to research that was going to become hot topic, I would give myself the same advice that I try to give myself now, which is to do things that you think are scary. If you think it's scary, that's a very good reason to do it. And if you can leave your comfort zone, do it. And opportunities will not often come to you. You have to go out and seek opportunities.
I like that last one in particular. I like all of them, but that last one in particular, I think is...
I try to live by these things. Sometimes I'm a bit too tired and prefer to have a nap, but I try to live by these.
Awesome. Well, that's a great place to wrap up. So if our audience wants to learn a little bit more about you, is there anywhere that they can find you on the internet, on social media, anywhere like that?
Yes, so I am on Twitter. So my handle is Jennifer_Fowlie. So I can be found there. I also have a website that has sort of bare bones information about me and what I do, which is jenfowlie.com.
Okay, perfect. We will leave links to those on our own website, insideQuantum.org. So thank you very much, Dr. Jennifer Fowlie, for your time here today. Thank you also to the Unitary Fund for supporting this podcast. If you've enjoyed today's episode, please consider liking, sharing, and subscribing wherever you like to listen to your podcasts. It really helps us to get our guest stories out to as wide an audience as possible. I hope you'll join us again for our next episode, and until then, this has been Inside Quantum. I've been Dr. Stephen Thompson, and thank you very much for listening. Goodbye.